Hi everyone. In this video we're going to continue on with our stochastic processes material, and specifically we're going to continue on with things related to a Poisson process. Okay, and so sometimes when we have a Poisson process, before, what we were interested in were counting the number of occurrences that occurred or the probability that so many occurrences occurred during a given time interval. But we could also be interested in the time it takes until the next arrival or the next count or the next whatever for our Poisson process. And that time that it takes until the next arrival is called interarrival time. And so we're going to look at the properties of interval arrival time and see that the way that we can model this interarrival time is actually with a distribution that we've already talked about. So for a Poisson process, it turns out that the interarrival time can be modeled with an exponential distribution. Okay, in fact, it sort of works the other way too. If I have a counting process, which is a little bit more general than a Poisson process is a specific counting process. But if I have a counting process that has an interarrival time that's modeled by an exponential distribution, then that counting process is also a Poisson process. Okay, so it turns out we can use the exponential distribution that we talked about in chapter 4 to model these interarrival times. And so, unlike the Poisson process modeling, interarrival times are continuous in both measurement of the sort of random variable and in time. So if you remember, we had this two things that we were looking at, whether or not the random variable that we were measuring was measuring discrete or continuous things, and then we also had whether the time was being discrete or continuous. And so in this case, we have both continuous measurements and time, because the random variable, what we're looking for, is actually time now. And then the time part that we had before is a little bit weird. Okay, and so specifically, just as a reminder, the PDF of a exponential distribution looks like this, okay, where lambda is going to be the same thing as we used for the Poisson process. So that's the rate, okay, and so the PDF of the interarrival time is equal to lambda e to the negative lambda x, okay, and the CDF has a nicer form than, say, when we were dealing with the Poisson process. Okay, the CDF of interarrival times that are exponential is 1 minus e to the negative lambda x. Okay, now let's look at an example. How would we actually use this? Well, take this example. So we have a call center. Okay, and calls tend to arrive at this call center. Sorry, I've got to move my notes here. Calls arrive at a call center at a rate of 1.8 calls per minute. It should be calls, not call. Find the probability that the next call will arrive in the next 30 seconds. Okay, so to do that, calls arrive in the next 30 seconds. We have to now think about what kind of probability that we have in contrast to what we were doing with the Poisson process. So there it was counting process, so we were dealing with discrete things, and so we were counting up probabilities. But here again, we were dealing with continuous things, and so to find probability for continuous random variables, what we need to do is we need to integrate over the PDF to find a probability. Okay, so if x, so what do we know so far? We know lambda is 1.8 calls per minute. And we know that the random variable x is the time it takes for the next call to arrive. Okay, so a call just arrived, in a sense, if we were sitting in the call center. The call arrived, okay, great, it happened, and now we're interested in the time it takes until the next one arrives. So I'm sitting there and I'm waiting. These are often called like waiting times as well. I'm sitting there, I'm waiting for the next one arrive, the next call to arrive. Okay, and so that's what we're sort of doing. In the next 30 seconds, okay, means I'm going to take the integral to find, let's see, the probability that x is between, so it has to be greater than 0, and then it has to be less than or equal to some number. And here's where we have to keep in mind or keep track of the units of the problem. So if we look at lambda, it's in terms of minutes. Okay, but if we look in terms of x, or we look in terms of what I've asked, it's in seconds. So of course we have to change those seconds to minutes, and that's a half a minute. Okay, and so the probability that I'm interested in finding is the probability of that x is between 0 and 0.5. Okay. Now, by the definition of continuous probability for, probability for continuous random variables, I find this probability by integrating over the PDF. Okay, and so I'd integrate from 0 to 0.5 of lambda e to the negative lambda x dx. Okay, and of course we could substitute those numbers in. 0 to 0.5, 1.8 e to the negative 1.8 x, okay, dx. And we could do that, but that's going to involve a little bit of interesting integration. You have to remember antiderivatives of e raised to the something. The antiderivative of e to the x is e to the x. And so things get a little bit interesting there. But what we can also use is a rule or a fact about the CDF, because I also gave you the CDF. And the rule about the CDF is that this probability can also be written as the CDF evaluated at 0.5 minus the CDF evaluated at 0. And that's much easier because we just have to sort of substitute in 0.5 and 0 into the CDF to get our answers. Okay, so if we substitute in 0.5, the CDF was 1 minus e to the negative lambda times x. Okay, so we have that minus 0. So technically it's 0. I'm going to flip back here to inter-arrival time. Oh, sorry. I gave us the CDF here, and the CDF for x values greater than 0, it's that function. But for 0 and less, or 0 and less, it's 0. Okay, so for our example here, the second part, f of 0, is 0. So all we need to do is find what is 1 minus e to the negative 1.5, negative 1.8 times 5. Okay, and so when we do that, so let me do that quickly on a calculator here. You can do that as well. It'll be good practice for when you have to do it in the your turn that's coming next. So negative 1.8 times 0.5 is negative 0.9, okay? And e raised to the negative 0.9 power is 0.406 or 407. So really we've got 1 minus 0.407, and 1 minus 0.407 is 0.593. So the answer to this question is there's a around 59.3% chance that the next call comes within the next 30 seconds. Okay, which if you almost get 2 calls per minute, that makes sense, right? On average, you're going to get 2 calls per minute, which maybe is 1 call per 30 seconds. And so there's about a 60% chance that the next call comes within the next 30 seconds. Okay? So hopefully that wasn't too bad. And so here's a your turn that does about the same thing. So customers come into a certain store at a rate of 2 customers per minute. Find the probability that the next customer comes between 45 seconds and then 1.5 minutes. Okay, so you have to change 45 seconds to 3/4 of a minute. Okay, and so it's basically the same problem as the last time. Instead, the rate is 2, and you're now integrating between 0.45 and 1.5. Okay, so that's the end of this video, and almost, or pretty much the end of our stochastic processes section of this course.